cell phone. Better? Yeah, check. This is good. Did you guys hear me at the back, by the way? You could hear me, right? Okay. Cool. Did you miss the first part, or did you still? Okay, good.
It's actually worse now. Yeah.
Okay, cool. I'll just put it here. Yeah, so I hope this still works. This works? Okay, great. It works for them. Cool. Yeah, so I was talking about precision agriculture, how it could be a big disruption because it helps farmers be more productive. They can get more yield. It helps them save cost. It's also better for the environment regarding climate change and things like that because you're not wasting water. You're not putting in more nutrients, more pesticide. The thing is, precision agriculture as a technique was proposed back in the 80s. It's been 30 years since then, and this technology still hasn't taken off. And the biggest reason this hasn't taken off is the cost of existing data-driven agriculture solutions. Just to give you an idea, I was at an expo here in California. There were lots of companies presenting their latest and greatest precision ag equipment, and the cheapest sensor package that was available there in that expo were 5 sensors for $8,000 and a recurring cost. For most farmers, this is a lot of money. That is 5 sensors for $8,000 when you don't know what is the ROI. What is my return of investment if I'm going to put in 5 sensors? So that is the goal of the FarmBeats project. The goal of the FarmBeats project is to bring down the cost of these solutions by 2 orders of magnitude. We want to bring it down from 8,000 to 80. And I'll talk about some ways in which we can get there. But before that, I wanted to talk about if the goal was to build a map of the farm. So lots of people have looked at sensor networks for agriculture and so on. If I gave you guys the question, or any computer scientist or electrical engineer this question, that hey, this is a farm, I want to build a map. Say, what is the soil moisture throughout the farm? Well, most of you would say, you know what, this is an IoT problem. We know how to solve it. What we're going to do is, if this is a farm, I'm going to put lots and lots of sensors, get them connected to the internet, and well, push it to the cloud, you have that map, right? You could just put in lots of sensors. This is something that would theoretically work, except in the context of agriculture, we run into key challenges. The first challenge is that of internet connectivity. Most of these farms, even in the US, you see these maps, beautiful maps from carriers saying, hey, we have X 97% of the coverage. Once you go beyond the cities to any of these farms, you do not have coverage, not even edge. So most of these farms do not have internet coverage. And further, what makes it worse is, even though sometimes internet connectivity might be present when you plant the seeds, by the time the seeds grow, the connectivity is lost. The second challenge is power. Most of these farms, they don't have a power outlet. You need to somehow get them to work. They would use some of your solar panel innovations. Solar panel is one of the alternatives we are looking at, Eli, but one of the challenges with solar is, well, you have to live in Seattle in winter to realize why things might not work. We get a lot of rain, a lot of cloudy days, and there are some innovations that we had to do in that space as well. And the third challenge is that of limited resources. So suppose the question was that you wanted to build an accurate soil moisture map throughout the farm. If you wanted to build an accurate soil moisture map, you would need to put lots and lots of sensors, say a sensor every 10 meters. But putting a sensor every 10 meters is expensive to deploy, to manage. It will come in the way of the farmer as the farmer does the day-to-day job. So these are the questions that we answer as part of FarmBeats as well. FarmBeats is an end-to-end Internet of Things system using which we're able to take data from sensors, drones, cameras, and push them to the cloud, and in the process solve some of these hard problems that I just introduced. And I'll go through some of them in this talk. So the first challenge is that of internet connectivity. The challenge is as follows. So the farmer's house has, most farmers, I'm talking here, I'll primarily talk of the developed world here in the US. I'll extend it to the developing world as well, and if you have any questions, feel free to ask that. So the key question of internet access is, most farmers here, they have some sort of connectivity to the cloud. They pay for broadband, they get 1 to 3 megabits per second, but they have some sort of connectivity. The actual farm could be a few miles away. Even though, as I mentioned, even though connectivity might exist, when you plant the seeds, the connectivity might disappear when the crops grow. So the question is, how do you provide connectivity from the middle of the farm to the farmer's house? To solve this problem, we use the approach, the solution that I mentioned initially, the TV white spaces. So this is something where Berkeley, BWRC, and Anand's team have done some amazing work in this space. At Microsoft too, we were working in parallel and collaboratively in a lot of these projects. The key thing, just to introduce this concept to a lot of you here, what the TV white spaces enables is a scenario where, imagine if you go, say, to Best Buy and buy a Wi-Fi router and put it in your house. Imagine a scenario where you could access your Wi-Fi connection a few miles away. That would be cool, right? Right now, as soon as you go outside your house, your Wi-Fi is gone. The key way we did this was we took a Wi-Fi signal. This was work for which we got the Best Paper Award at SIGCOMM, was we took a Wi-Fi signal and put it in empty TV channels. This is over-the-air TV, TV you watch using antennas. You know, when you browse over-the-air TV, on certain channels you get reception. The other channels, all you get is white noise. There's no channels, no reception there. With this technology, you can put Wi-Fi signals in those empty TV channels in a way that doesn't interfere with your reception in an adjacent channel. So you could be watching, say, channel 7 at home. On channel 8, we could be sending Wi-Fi signals. And the reason this is so cool is that compared to Wi-Fi at the same power level, in UHF TV channels, you get 4 times the range, just based on physics, right, and bigger antennas. In VHF, you get 12 times the range. And this is purely based on physics. Once you put it out there through crops, canopies, and so on, you get much better range. Just to give you an example, we were comparing a 900 megahertz signal in a almond orchard in California near Bakersfield with 900 megahertz technology using the same modulation, everything else. We were getting 2 kilometers of coverage. Using the TV white spaces in VHF, we got 20 kilometers, 12 miles of coverage. So with this, now suddenly you can start covering really large distances using the TV white spaces technology. So at a very high level, I wanted to introduce this concept. This is not accurate, and I can point lots of flaws in the thing that I'll say, but this is just to introduce at a very high level what the concept is to the people who are not deep in this space. So at a very high level, what this does is we are using a concept called dynamic spectrum access. Right now, for example, on your phone, as soon as you turn on Wi-Fi or cellular, your device can start transmitting. It's no longer the case here. Here, for example, if the x-axis is frequency and the y-axis is power, the way the system would work is your device, say your cell phone or your laptop, would first scan the spectrum to see what channels are available, the red ones. The red ones are not available, there are TV transmissions there. It would start operating in an empty channel, that's at that location. At the same time, it keeps monitoring to see if the transmitter came back. If it did, it would move to a different part of the spectrum, and if needed, adjust its bandwidth and power level as well. So there are lots of papers written on this. Even on our site, you'll find each one of these has multiple papers. We had to do this to convince the FCC, and there are lots of papers on Anand's site as well. You should go check it out, on just convincing that this technology can work in a way that doesn't interfere with the primary users. And we got back in the day in 2010, the FCC chairman actually come to Microsoft campus as well, Chairman Janachowski, to see the demo we had put together on Microsoft campus. This was approved in the US. This was made legal in the US in 2010. Since then, at Microsoft, so this is, as I was saying, at Microsoft, there's a program that I had started along with some of the people in the team called the KNOWS Program, where through the years we've actually done a lot of work taking this, showing that this can actually work, extending it to different countries, which is still ongoing. And we built some of the first white space radios, built a Wi-Fi-like protocol, Wi-Fi, which got the Best Paper Award, built the first network. And since then, we've actually gone out and worked with several countries to deploy this technology to connect high schools, libraries, hospitals, all that to the internet, just connecting a lot of people that previously were not connected to the internet. In India, for example, one of our longest links that we have is a non-line of sight link going 16 kilometers, that's 10 miles at 2 megabits per second. This is to a high school in a place called Srikakulam, where this place did not have power, did not have any internet. These students hadn't gone to the internet before, and we were able to connect them to the cloud. Same in Kenya. We get a lot of messages from people in Kenya who we were able to connect, and we're getting a lot of support from Microsoft in this as well. This is all Microsoft-sponsored pilots at different places around the world. In fact, on Windows 10 launch day, our CEO, Satya Nadella, was in a white space site satellite installation site in Kenya, Skyping to a school in India, showing the capabilities, and these guys were upgrading to Windows 10 over the spectrum, right? So this is something which we are after connect. This has now been made legal in various countries worldwide, in US, Canada, UK, Singapore, Philippines, South Africa, Malawi. Several countries have passed regulations around this, and we're working with the other countries as well.
What are the frequencies? So
this is the TV channels. So we typically use TV channels 54 to 88, and then it's 174 to 216. This is in VHF, and 470 to latest it's 614 megahertz in UHF. Yeah. So this is just showing what the TV whitespace spectrum is in Seattle, right? So if you turn on a spectrum analyzer, those are the channels that are used. The others are not in use. So I already talked about the benefits of Wi-Fi and Zigbee. The key insight in the context of agriculture was that, and when I was talking to Jan Rebay today, he was saying that, you know what, when you're all doing the white spaces work, the key pushback was, well, there is spectrum where no one really wants it. Well, that's true if you wanted to provide connectivity in cities, but in farms, it's actually the opposite. The thing is, the TV towers are where people are. People are the ones who watch TV. In San Francisco, you'll have the TV towers. In Seattle, you'll have it. The farms are usually away from the cities. So if you turn on a TV in the middle of a farm, most of the channels will just be vacant. You'll actually get very few channels. The more empty channels there are, the more unused spectrum there is. Just to give an idea, we did an analysis. Typically in the US, in the middle of a farm, you'll find around 30 TV channels available. 30 TV channels, each TV channel is 6 megahertz wide, is 180 megahertz of spectrum. Typically, you'll multiply by 3 to convert it to megabits per second, just to get some rough numbers. We're talking of more than 500 megabits per second of unused capacity out in the middle of the farm. At which point, we're not only talking of connecting sensors, you could be connecting drones, cameras, getting a lot of data that you previously just couldn't gather from the middle of the farm. In fact, when we talk to agricultural scientists, this is the #1 problem they talk about. That is, how do you get data from the middle of the farm? With this, we believe we have solved this problem. Our vision is just like Wi-Fi connects your house, the TV white spaces spectrum can be used to connect your entire farm, and that's what we've been doing in multiple farms around the world, where we put in this antenna and miles around it gets connected, streaming a lot of data from drones, tractors, cameras, and so on. So this is the first challenge, connectivity. The second challenge is that of limited sensor placement. I talked about the goal being to build these accurate maps of the farm. What is the soil moisture map throughout the farm, 6 inches below the soil? What's the soil temperature map? If you wanted to build maps like that, as I said, if you wanted to build, say, a soil moisture map, you would need lots and lots of sensors, which quickly drives up the cost. Say a sensor every 10 meters to measure soil moisture at different depths, your cost will quickly go up. It's costly to deploy, to manage, it will come in the way of the farmer. So the key question is the last bullet there. Can we build an accurate map using very few sensors? And one of the things Eli mentioned is, well, and this is one of his relatives does that, and this is something which, actually not Eli, it wasn't you, it was Christoph in my first meeting today. He mentioned that one of his relatives does soil sampling in the middle of the farm. That's the state of the art. A little more advanced farmers, what they do is, if they have to build a soil moisture map, they'll put a few sensors and then use a technique, either linear interpolation to predict what the values are in other parts of the farm, or a technique known as Craiging's method. Essentially, it assumes it's a Gaussian distribution and predicts spatially how this variable varies throughout the farm. That's also known to be very inaccurate. The question is, can you build better maps? To do that, we use UAVs. These are drones that can cover large areas. You can get them for $1,000. They have a camera at the bottom, and they can keep taking images of the entire farm. The key technology we built was, in addition to the spatial interpolation, we added another machine learning model with the key insight that if two parts of the farm look similar, not only in RGB but in multi-spectral as well, they're likely to have similar values. And we encoded this in a machine learning model. So now you have two machine learning models running parallelly, one saying that if doing spatial interpolation, that if two parts of the farm are close to each other, they're likely to have similar values. And the other machine learning function, which is saying that if two parts of the farm look similar in RGB or in multi-spectral, they're likely to have similar values. And this is something which we showed to be, and I'll show later, to be very accurate, 3 times more accurate than state of the art. Just digging a level deeper, the way the system works is the drone flies, it starts getting those kind of images. From here, what we do is we build a 3D point cloud model of the entire farm. This is a 3D model by stitching them together using photogrammetric techniques. And then what we do is, based on the 3D model, we then do the stitching of these images to create those kind of maps in various bands as well as in RGB. Right, so these maps then are stitched together over the entire farm using various techniques. There are many other companies which do this too, and we're using standard techniques with some optimizations to make it run faster. The thing is, this kind of imagery technique using drones works well in the developed world. With the Gates Foundation, we are actually working in the developing world as well, taking the same technologies that I'm talking about here to places in India and Africa. Well, drones work well in places like the US and in the developed world. They don't work that well if you go to the developing world because of some of the challenges. One, they have limited battery life. That is, most of these places don't have a good way to charge these drones. So, and the most state-of-the-art drones that you can buy, even from DJI, they last 30 minutes, they won't last anymore. How do you get longer term aerial imagery? The other challenge is they still cost over $1,000, which could be very expensive for the smallholder farmers in India and Africa. And the third interesting problem is that of regulatory concerns. That is, in one country where we wanted to use drones, in order to use a drone, we needed to get permission from the Ministry of Defense. Well, at that point, it's not going to happen. So then, how do you get long-term aerial imagery in these places? Our technology is very low-tech. That is, we use helium-filled balloons. These are like biggish balloons, around 4 feet, 5 feet in diameter. We built a mount, the one you see here, where a farmer can put their smartphone with the camera facing down and a battery pack. And this thing can stay up from 4 to 7 days taking images for the same part of the farm. One of the graduates from here, Vasuki, she was working very closely on this, and Girija as well. We worked closely with both of them. So this is a very interesting, and this is tethered to the ground, going up 150 to 200 feet. The farmer, there's a farm about 25 miles east of our Microsoft campus in Seattle. The farmer there uses this for long-term aerial imaging of the farm. As I said, this thing can stay up from 4 to 7 days taking images of the farm. The farmer there runs into the problem, because he lives in Seattle next to a river, every winter his farm gets flooded. Based on regulations right now, so the farmer cannot sell any any crop that is touched by the flood. So right now what he has to do is every morning if he sees any amount of flood, he's going to throw away all the crop in the farm. With this technology, he can actually monitor, he has visual proof to see which parts of the farm were actually touched by the flood, and only throws away those crops. So this is one scenario. The other scenario which we built for India and Africa is someone could just walk around with a balloon, because labor is inexpensive, put it on a bicycle and so on. And then we had computer vision techniques to basically stabilize the imagery to build these kind of aerial maps of the entire farm. The key challenge there was that in the case of a drone, your image is stabilized. In the case of a balloon, your balloon moves around with the wind. So one of the ideas that we had was using a gyroscope, and then because these phones have a gyroscope built in, so you can then see when it is actually facing down and use those to do the keyframe extraction based on that, and then use that to do the stitching. And there are several other innovations as part of this. What interesting there, I would love to hear insights from people here about how you can make it even cheaper than the technique I presented before. Because in a way, if you think of it, for the farmer incarnation, that guy's problem, right? He wants to do long-term aerial imaging of the farm. Other than the approach that we have, there are no, you could use satellites, but with satellites you'd be lucky to get even a snapshot every day. You could use drones, but drones don't last more than 30 minutes. This is just a low-tech technique where all you do is just fill up the balloon, put this mount, put your smartphone, send it up, and you start getting images. We presented this to Bill Gates. His feedback was, well, let's start thinking about methane, because helium is one part, where how do you get helium to the remote farms? We have done this in India in a place called Anantapur, which is a small village in Andhra Pradesh. We've been able to work it out there, but worldwide, the interesting thing is a lot of methane is produced by farms. So can you actually leverage that to get, well, methane is inflammable, that's one of the issues, but that said, it's abundantly available in farms. So we're still investigating that. That's still a research theme that we are investigating. So going back, how do we build those maps? So we take aerial imagery from drones or balloons, we create these kind of maps of the entire farm. Then, based on the few sensors that are distributed, we build a machine learning model. We train the machine learning model based on the sensors, and then we use that model to predict what these values are in other parts of the farm. We've done this for soil temperature, soil pH, and soil moisture. This is digging a level deeper. The training data is coming from the sensor. So what would happen is, every few weeks, you would fly the drone or take the balloon, you'd get the image. based on the sensor readings at those locations, that's providing you the training data for when you captured the data. You use that to train the model, and then you use that model to predict what these values are in other parts of the farm. Now, of course, we can improve the predictions, and this is something, again, we'd love to get feedback on where we are, how do you improve it. But this is the first time we believe anyone has been able to combine imagery from drones with sensors to build these maps. One of the interesting side benefits of doing what I just suggested is that typically when you fly a drone, in a 15-minute drone flight, you're generating over a gigabyte of data. You can't ship the gigabyte of data to the cloud from the middle of the farm. The compressed image is a panoramic overview. The stitched image is still a few hundred megabytes. But if all you ship to the cloud is the machine learning model, that's just a few hundred kilobytes. That's the only thing that you need to send to the cloud right away. So as I said, the key thing here is that there's a lot of work in the startup community on using sensors. A lot of people use drones. We believe we are the first who's been able to combine both of them in a meaningful way. And once we showed the capability of doing this for soil temperature, soil pH, and soil moisture, we were approached by the ag companies to do this for the other parameters as well, for leaf wetness, evapotranspiration, and so on. So the third key challenge, so these were two. With the TV white spaces, I showed how you can bring down the cost of each sensor. With the second one, I showed how you need much fewer sensors than what you would otherwise need to build very accurate maps of the farm. The third challenge is that of limited internet access. That is, with this, you can send a lot of data with the white spaces to the farmer's house, but the connectivity from the farmer's house to the cloud is weak. As I said, most of the farmers in the US, they pay for broadband, but what they get in the farm is just 1 to 3 megabits a second, which is not a lot. Imagine sending gigabytes of data from drone imagery to the cloud. It's not going to happen. It's also, the connectivity is also prone to outages. So there's a farm in upstate New York where we've done deployments, and every time there is a snowstorm, there's a high likelihood that his internet connection goes off. So the key question then is, if you're gathering all this data, but you don't have a good connection to the cloud, how are you going to provide all the benefits of all this data to the farmer? So to solve this problem, so before actually we went to solve this problem, we went around and did a survey. We talked to agronomists, we talked to farmers, we talked to extension agents, professors in ag schools, and asked them the question that if you could build maps like this, if you had the capability of FarmBeats, what kind of services could you provide on top of that? I'll walk you through a simple example. So these are the different sensor data streams that we support, some of them. We take weather data, video data from drones, image stream from cameras, different types of sensors, soil moisture, temperature, and so on. We also have an app for the farmer. So the farmer takes notes, that sensor data as well for us. So based on this, I'll walk you through a simple example of a service that we provide. So you can take the video from drones and create the orthomosaic, the stitched image that I had just shown from the drone images. You can take data from sensors and do this interpolation that I also presented to build a heat map, say a moisture heat map of the farm. You can then take the predicted weather forecast, you can predict that, and feed it to build a precision irrigation system. That is, you can then use that to decide how much water do you apply where in the farm, if you have the heat map, if you have the weather forecast. This is just one such example. You can actually think of many such scenarios that you could build on top of this. In fact, once we started talking to farmers, this slide is about 2.5 years old, and every time you present it to a customer, I mean an agricultural company, they come up with new use cases of what all they can build on top of this infrastructure. So the reason we went through this exercise of going through all the services was to ask the question, how much data is generated on a farm and how much of it is needed in the cloud? So this is a farm in upstate New York. On an average, this is the amount of data that we're generating on a daily basis. Well, shipping all this data to the cloud is going to take forever. Like gigabytes of data, say 10 gigabytes of data from the farm to the cloud, it's going to take forever. Well, you don't really need to ship all the data because different services have different latency constraints. For example, if all you wanted to do was query the sensor data, that's you want to know what's the temperature in the barn right now, what's the soil temperature right now, you want that information right away. If you wanted, the second one is livestock monitoring, if you can see clearly. For a farmer, if they wanted to see if how their livestock is doing, again, they want that information in near real time. There's kind of a funny story, not that funny for the farmer, but there's the farmer in Eastern Washington, the one we work with, actually the one close to Microsoft campus. He's a smallholder farmer. He sells his produce to the restaurants. And he runs into this issue that every year, just before harvest, there's a black bear, not a wild bear, a bear that comes and eats up all the red lettuce in his farm, doesn't even touch the green lettuce next to it. His point was, can you send me a notification whenever you see the bear in the farm, and he'll come and scare it away with a gun or whatever, but he needs that notification right away. If send that notification a few hours later, well, that's of no use. The bear has done its damage. So then, though that's another scenario where you want the information right away, right? That's a classic machine learning problem. You have this data, camera streaming data, which you need to run the ML on it and send the notification. For the others, if you're doing irrigation scheduling, you could wait a few hours. For pest inspection, you could wait a few hours, even a day. For a variability analysis, what do you plant where in the farm, you could wait a few days, even a week, and the farmer's okay with that. So in the typical world, as I said, you would send all this information to the cloud, do this analysis in the cloud, and send it to the farmer. Well, you can't really do it in the case of agriculture because of these problems I talked about, weak connectivity and lots of outages in the farm. So our key insight to solve this problem was that most farmers have PCs. If they don't have a PC, we ship them a PC form factor device that runs Azure IoT Edge. And that does a lot of compute sitting in the farmer's house and then sends summaries to the cloud, where we then merge with various other data streams from satellite data, weather data, to then provide an analysis and recommendations to the farmers, to the agronomists, and so on. Just digging one level deeper, everything you see inside this big blue box here is running in the farmer's house or office. It takes data from sensors, from drones, it does the orthomosaicing, the stitching on the edge itself, uses that to generate heat maps. This heat map then flows into these ag services. The ones in blue are the ones we build, the other ones are the ones we are actively working on, which are then all running on the PC itself. All this data is lazily synced with the cloud. We also support cameras, streaming data again over the TV white spaces, where we are doing deep learning at the edge itself. The other interesting thing we do is, sorry, I don't know what happened here. Yeah, so this, as I said, the sync and run offline. We have a web server that's running here. You can log into the web server. You can see what services are running. We have unique storage. That is, every time you fly a drone, as I said, you generate gigabytes of data. Rather than shipping the gigabytes of data to the cloud, this gigabytes of data sit here at the edge. What this leads to is a very interesting architecture where right now you hear a lot of people talking about the edge, right? The internet edge is a buzzword in the industry. The way people define the edge is a subset of the cloud. That is, you have X services in the cloud, the edge is running a subset of them. Here, what we realize is this is actually leading to a new definition of the edge, where the edge is no longer a subset of the cloud. Because you have unique services that are running on the edge, because you have unique data that resides on the edge, you have unique services that could be running on the edge. In this case, for example, because the high-res drone imagery is generated in the farm, we keep the high-res drone imagery only on the edge. We send the transcoded images to the cloud. Say you'll convert a 1 gigabyte file to a 50 megabyte file and send it to the cloud. But because the high-res drone imagery is on the edge, you can start generating you can start thinking of new kinds of services that are built on top of that data. One such service we built is a 3D walkthrough of the farm. That is, if you're connected to the edge, you could have an immersive experience of scouting the farm because you have this really high-res image of the farm sitting at the edge. So this now leads to, if you think of it, now if every edge, your phone, if every computer started offering these kind of unique services, you can see how the architecture of the internet needs to be thought about as well. How do you discover all the services around you? How do you reduce the latency, security? All those issues start coming up if you start thinking of this definition of the edge.
Is the 3D walkthrough using exclusively data coming back from the cloud, or is it using some of that local?
It's only using the local data. It's only using the local data. Because, so what we do is, as I had shown earlier, if you get the high-res imagery from the drones, you can use it to create, we create a 3D point cloud of the entire farm to create a 3D model of the farm. And that's done, we're able to do that because we have the high-res drone imagery. And because of that, you could have a 3D walkthrough of the farm if you're connected to the edge. So you can imagine wearing a HoloLens or a VR device and having a very immersive experience, and you get that only on the farmer's house or office. You don't get it in the cloud unless you transfer all this data to the cloud. Yeah, in fact, at Hannover Messe, there's a big manufacturing conference, Ernst & Young, which is our partners, was showing how you could build this kind of an immersive experience once you have all this data. So this is one of the services which is, again, available on the edge, but while we are providing this edge right now as a device that can be set up in the farm, this entire problems of discovery and scaling this out, if every device started offering this service, well, that's a research problem that needs more thought. The other interesting thing about this architecture is that every blue box you see here are Docker containers. So I was presenting this at this talk at the National Corn Growers Association event, and there was a startup based out of the Valley which were like, hey, we have this really cool software, which camera and the software that runs on it, which is able to then, they're able to do very cool analysis in near real time based on that data. What we were able to do is, because it was because they were running on Azure, we were able to Dockerize it. And if you're able to Dockerize it, we are then able to move it here and put it as part of the FarmBeats pipeline and start exposing it to our customers. So this is a way we work with startups. So we're able to, if someone has any component without getting access to the source code, as long as they can Dockerize their component and comply with the APIs that we have, we are able to then put it as part of the FarmBeats device, FarmBeats Edge, and start exposing it through the web service to the different customers. So yeah, you hear, that's why I was saying, you hear about a lot of edge devices people talk about. We think we are unique because of some of these components on the bottom left of what all we can do with this system. The fourth one, which I won't get much deeper into, I know, Eli, you've done a lot of work on this on power, but just presenting some of our solutions here at a high level. So one problem I talked about was, how do you get solar panels to last for a certain period of time without putting huge amount of capacity out in the middle of the farm? So this was a challenge we ran into in Washington State. That is, if we ran an entire system on all the time, because we had this white space router, cameras, and so on, our system with the same equipment setup lasted four cloudy days. So how do you get it to last longer? So what we did there was, we put a small Raspberry Pi form factor device in the farm that looks at the predicted weather forecast, and based on the predicted weather forecast, it duty cycles the entire components. So if it's going to be cloudy, it's going to take camera snapshots every minute instead of every second. And we started making the system gracefully degrade based on the predicted weather forecast. And different components, we would duty cycle at different rates based on the importance of each of the components. So this is something we talked about in the NSTI paper. The other challenge which we're working on with University of Washington is that of using RF power to power the sensors. That is, because we have our own white spaces antenna sitting in the farm, can we then direct power from those antennas to the sensors so that these sensors don't need batteries anymore? Right? That would be another thing that we're looking at. And the third one, which is actually very interesting, was we came up with a way to improve the battery life of drones. One of the things I mentioned is, right now with most of the commercial drones, they last, say, 30 to 40 minutes. 40 minutes would be a stretch. How do you get them to last longer? So the key thing we built for this, the key insight here, was that we started leveraging wind to improve the battery life of drones. In particular, what we did was, the algorithm that we developed was to change the yaw of the drone based on wind, so that you use the wind to accelerate and decelerate the drone. And what we showed was, if you use this technique when wind was between 5 and 15 miles an hour, we got up to 30% improvement in drone battery life. This was work we did along with Purdue. My intern was from Purdue, and we published this at NSTI. So the way the system works then is, on the drone flight path, you would say the endpoints and you'd come up with the flight path, and then you start measuring the wind as you're flying, and then keep changing the yaw of the drone based on whether you want to accelerate or decelerate. And that results in an improvement in battery life of the drones. Of course, 30% is still, you would go from, say, 30 to 40 minutes, but you're still not solving this problem of going for days. But at least this is a step in the right direction. So I'll talk about a few of the deployments that we've done and how the farmers are using the system. So these are several deployments that we've done worldwide right now. Some of them are planned, some of them are already operational, quite a few of them commercial. So it ranges anywhere from 5 acres to a few thousand acres. We've used, these are some of the sensor boxes that we use. And just some statistics, this is the one that we're really proud of, that even though there was a week-long outage of internet in the farm, we were able to get the system up and running. We didn't lose any data, and all the services were still being provided despite this outage. This is one of the use cases that we have. Is what we built is, once you start getting sensor data from the farms, we are looking to, so we are also predicting, for example, soil moisture and soil temperature in advance. So right now farmers, all the tools that they have is they go to weather.com or any site, and it will tell you whether it's going to rain or not, what the temperature is going to be. It doesn't tell you what your soil moisture is going to be in the next, say, 5 days or 7 days. What we did to solve this problem was we looked at weather data from 50 weather stations across Washington state, and then over the last 7 years at every 15-minute intervals, and we used that to train a machine learning model, which we then do transfer learning for each sensor in the farm. We then apply that model. Within 24 hours, we start making predictions, and this is showing the amount of error that you get for soil moisture and soil temperature based on that. So this is one of the services. If you think of the gateway box, this is one of the services we provide to the farmer. This is another use case. This is a 4-kilometer stretch in upstate New York. The farmer wanted to know how his cows are doing once they're out in pasture. So we flew the drone. We transmitted the data over the TV white spaces to the edge device, where within 30 minutes because you have to stitch the drone image and so on, we were able to flag things like the grass is growing back well from left to right. This is a water puddle that needs to be fixed before the next planting season. The cows are pooping well, which is important information for the farmer as well. This is deep learning on cow poop, right? So this is where the cows are. This is a stray cow that needs to be herded in. All of this information within 30 minutes of flying the drone. The state of the art, if you had to fly a drone, is you'd fly a drone, you would take the SD card out, typically go to a city, upload all this to the cloud, wait for 24 hours before you get feedback. By that time, the stray cow would have moved somewhere else. With this, all of this information you're getting within 30 minutes. And as part of this, we actually just signed in May, we announced a partnership with DJI, which is the #1 drone company in the world, on integrating FarmBeats with DJI. So we are tightly working on transferring the data, doing the analysis on the edge based on the data that DJI collects. This is the farm in Carnation. This is 25 miles east of Redmond campus. We've been working with this farmer since 2015. We show him these beautiful pictures of the farm. We overlay this with data. For example, this was a soil moisture map where we were able to flag that this part of the farm is moist, even though we did not have a sensor over there, using the sensor fusion technique I talked about. This is a pH map of the farm. This is after the farmer had applied lime. We were able to flag that these dark parts of the farm are still acidic. He needs to reapply lime before he plants the seeds. The key question you would ask is, how accurate are these maps? So what we did was we went and collected 1,000 measurement points from 3 different 5-acre plots. This was done manually. I was there in 3 different 5-acre, 1 in Carnation, 2 in upstate New York. And then we asked the question, if we took just 10 of these points, how accurately can we predict the remaining 990 points in the farm? And we did that for soil temperature, soil pH, and moisture. And this is how accurate FarmBeats was in predicting the remaining 990 points. And this is how accurate the actual sensors were. That is, the sensor we used for soil temperature was reporting temperature in 1 degree Fahrenheit. The one for pH was in units of 0.2 and moisture in units of 0.5. So what we are claiming here is not that we are more or less accurate than the sensor themselves, but that the results are so close to the actual values that they are actionable by the farmer. Compared to, so in the research paper that we wrote on this, we compared this with state of the art, the Craiging method, and we showed that for the same data set, we are 3 times more accurate than what the Craiging method predicted. In fact, just to give more concrete numbers, for the same data set, we showed that Craiging's had a correlation of 0.2, ours was a correlation of 0.66. Still not 1. I know we can improve the machine learning algorithm, but it is much better than what Craiging's could do. When we gave it out to the farmers, these were some simple scenarios that the farmer wanted to use it for. The farmer in upstate New York, he has 8 refrigeration units. He started putting these sensors, and for us it was an easier problem, because one of the problems they run into is someone leaves the door open and all the produce goes bad. And this is actually a real problem. I was just meeting one of the CXOs of a big dairy organization from New Zealand just before coming here, and he was talking about the same problem. That is, there's a huge amount of loss because people leave the refrigeration units open. With this, it was a simple problem. You just leave this running. You can then run simple anomaly detection on top of it to flag that the door is open. The reason right now it's hard is still because of the cost of sensors, and these refrigeration units, they're so well insulated. They are like Faraday cages. It's hard to get signals out. We do put white space devices. So this is like a white space radio that we have, which has a tri-band radio, which you'd attach a sensor to, well packaged, of course, and you can then start it to report a lot of data. This is a deep learning scenario where we have have cameras in 3 different barns, streaming data over the TV white spaces. We can then at the edge start analyzing how many cows are there, whether they're moving well, whether the cow is sick, and starting to flag all that information. Again, because you have cameras streaming data over the white spaces and you can compute at the edge itself. So at a high level, that's what FarmBeats is. FarmBeats is a way to gather a lot of data from the farms using the white spaces, using the edge, and then apply the latest AI and machine learning techniques on top of it to make that data actionable by the farmer. And of course, with the FarmBeats work, we are still scratching the surface. There are lots of open problems if anyone's interested. And this is where I think a lot of the technology that we build in computer science would be applicable to agriculture as well. And I can get deeper into it. I know as computer scientists, we think of agriculture as one vertical. That is, you could take the same techniques and apply to many other verticals, retail, finance, mining. Agriculture is just one vertical. If you talk to the agriculture people, I was talking to an ag tech VC last Friday, and he was saying, you know what, agriculture is a horizontal where tech is a vertical. All the others are verticals too. So for us, the opportunities are huge, not just to change agriculture here in the developed world, but also in the developing world. These are some of the first few farmers we worked with, all 3 of them, just amazing. And you can learn more about it on our website. We do publish, and if you're interested, we are also hiring both interns and full-times. Do get in touch if you're looking for opportunities to work on this. Thank you.
Questions?
So for the photographing using balloon, don't you run into an issue that it's not very stable?
Yeah.
How do you take care of that?
So stable in the mobile case or the stationary case?
Both. I'm trying to do that with a camera on a balloons, and it's not stable at all.
It's not stable. So that's why we have done some things to make the balloon itself stable. The other work we are doing is, of course, in the computer vision machine learning side. We have some compute that we are putting up there. Like one of the problems we're looking at was, which we're writing a paper on, was how do you detect that because your camera is moving, how do you detect that there is a certain image that is moving as well? That is a farmer moving or a car moving or a cow is moving within the frames when the frames itself are not constant, right? There's a moving camera. So there we had to, one of the things we're doing is first stabilizing the images as much as we can. The other challenge is we're doing onboard compute where we are actually aligning the images and looking at the overlapping parts and doing computation on top of that.
So one thing that one of the architecture professors from Berkeley has done, which is in the same line, is kite aerial photography. So using a kite to take pictures.
The kitoons, Yeah, we have looked at kites too, and we have been thinking about that, especially for not for the stationary case, but more for the mobile scenario where someone could put it at the back of a bike, which would create the wind and do it. So that's something we are looking at as well. Balloons were very simple for us to do, but kites is something that we're investigating too.
I thought you mentioned that there's a gyroscope on the cell phone. And would that help?
Yeah, so that helps stabilize the imagery. That is, we're only looking at when the camera is pointing down so that you don't run into racing issues.
When you were talking about the precision images and how you use machine learning to predict from sensors what the farm conditions will be like at a small scale, made me, one thing I thought about then is, of course, part of the problem is where do you place the sensors? And that looks to me a little bit like a clustering problem where
that is,
trying to take little regions of the farm and cluster them into units that can be predicted by a single sensor. Can you say a little bit about that?
No, that's a very important problem. So that's a very important problem. Before we go to a deployment, we actually run an algorithm to do sensor placement. We get imagery, aerial imagery from the farm, preferably multi-spectral. And then what we do is we do run, instead of clustering, we run a segmentation problem. It's like you segment it based on, so essentially the input to the problem is how many sensors do you want to deploy? And based on that, we then do segmentation, just kind of clustering, to say these are the segments and these look similar, and this is where you should be placing the sensors. The thing is, just RGB based clustering is not good enough, because for some of the parameters that we are measuring, for example, moisture, for example, red edge band, not RGB, might be a good spectrum band to use. So we would run the clustering on the red edge band. We would run it on all the bands that are of interest.
Can you clarify what you call it, non-RGB?
No, beyond RGB, the multi-spectral bands. Sorry.
I'm just wondering which color that is.
Yeah, so this could be, so any of the ones I presented in near infrared or red edge or any of the other bands. So each band carries some signal. And we have an algorithm. Basically what we've done is looked at literature to see if you're looking for pH, there's a certain band that contains more information for pH. If you're looking for soil temperature, there's a certain band that contains more thermal information. And we done clustering on those images to say these are the places where you should be putting the sensors. And then essentially looking at an intersection. If I'm putting multiple sensors, this is the location where you should be putting it for most value. So essentially it's a value of information algorithm that is well known in the AI space is what we are applying here.
Okay. So on the subject of the multi-spectral, given that you start with a cheap camera, if you're lucky, you get 3 colors.
Yeah.
So how do you do multi-spectral with a cheap camera?
Yeah, no. So this is an interesting question. We actually, when I was presenting this at one of the Gates Foundation events, one of their grantees is CIMMYT. I don't know. CIMMYT is, they do a lot of research on rice in the subcontinent, in India, Southeast Asia, and so on. Those guys came up with a way where they can remove some of the filters from existing cameras to start covering additional bands. So that's one of the things that we're looking at. There's also some research that we are doing to train models, so that then you can kind of hallucinate if you think of it, but take RGB and try to predict what the multispectral bands would look like. So that's some other work that has been going on as well.
Right, and the other one is, I imagine that when the soil is dark, there's more water in it, so you're going to pick that up on the camera. But how do I pick up pH from a camera?
Yeah, so that's it, which was one of the interesting insights for us as well. There's actually some bands in the multispectral band space which actually worked out as good indicators for pH.
And which color, which wavelength?
I can email you. I don't remember on the top of my head. Yeah, one of the spectrum bands.
I see. We have more student questions here.
One major problem that farmers face is natural disasters, just drought or floods.
Right.
It really hampers the productivity.
Right.
So, does your technology have maybe ways to make farmers, their agriculture, more resilient in the face of those disasters?
We haven't gone there yet, but this would be a great next step. So we haven't gone into making them more resilient. So as you can see, it's mostly it's a data platform where we're able to gather a lot of data. One of the insights, now once you ask this question, I'm thinking of are there insights that we could make to predict these kind of things. One of the things, for example, we're doing is microclimate prediction. If we can say that, you know what, there's going to be so much rain that's going to cause flooding, if we can give that insight a few days in advance, then the farmer can potentially use that to be prepared for it. So that's one way in which they can be prepared. I don't know if we can avoid these disasters, but that I think would be the harder problem. Yeah. Yeah.
Hi, thank you for the interesting talk. I think I missed it, but could you speak a little bit more about the kinds of sensors and the power constraints that you were dealing with? Because you had Wi-Fi in there, which strikes me as a bit of a straw man given technologies like LoRa, technologies like Mesh 15.4, BLE supports meshing technology as well. And also, are the power constraints, are they driven by using things like a Raspberry Pi, which is like a whole 5 watts that's sucking on your battery? Or are you actually looking at duty cycling radios? Are the types of sensors that you're using particularly sort of wattage?
Yeah, I think you asked 2 questions. One was about the bandwidth, the other was about power. Yeah. So for bandwidth, we are using LoRa where available. So Brightspaces is not available worldwide, and in places like India and Africa, we do use LoRa because it's legal. In fact, this radio that we have, it does tri-mode communication. It will use either LoRa if you're operating in 900 megahertz, or it will use white spaces in UHF or VHF. And the particular example I gave is in this this almond orchard that we have in Southern California, next to Bakersfield, where we were able to get about 2 kilometers of coverage using LoRa. With the VHF TV white spaces spectrum, we are getting 20 kilometers, 12 miles. So those are just scenarios where the LoRa signal, yeah, it's great, but it doesn't penetrate through all the things that you want it to go through. In fact, some of our latest experiments, we put this in soil, and even under a meter under soil, our signals just keep going through. And that's useful for another whole set of other sensors and so on that we could do. So that, I guess, answers your bandwidth. So one one was the range question, the other is the bandwidth question. We're not using Wi-Fi, we're using Wi-Fi-like technology over the white spaces. That's needed if you're transmitting data from cameras, from drones. LoRa doesn't do it. LoRa will give you, say, 110 kilobits per second, 15 at best.
But the sensors themselves are...
Sensors, yes, but for drones, cameras, tractors, that doesn't work.
Sure.
So for that, we need higher bandwidth, and that's why we're using that. And that leads to the power question as well. Because we have such high bandwidth radios, is why you need power. When I said Raspberry Pi, I meant Raspberry Pi-like devices, not Raspberry Pi itself. So we're using another device. One from Upsquared is what we're using. We have other devices as well, which works as the device, as a controller device, which is lower power. But then the reason we run into power constraint is, one, we could always put in more batteries. Like right now we have 4 lead-acid batteries and they're in series, providing a 48-volt connected to a solar panel. We could put more batteries for it to last longer. We could connect more solar panels. But we wanted to see, given that constraint of these many solar panels, these many batteries, how long can we make the system last? So that's why we had to duty cycle everything. Duty cycle the radios, duty cycle the camera, duty cycle the white space radio as well, duty cycle the Raspberry Pi-like device. Everything was the router that we had. And the rate at which each one is duty cycled is not the same, because some of them are for in-farm communication, the others are for communication from the farm to the cloud. So each one had a priority level, and that's why we had, it was an optimization algorithm that we had to solve to make that work.
Okay, with that, let's thank Dr. Chandra again.
Yeah, thank you.